Okay. So this morning, what we're going to do is go over this program here that's on the right-hand side. It's relatively straightforward. It's just got one function with 3 variables in it, each of which are initialized to hex values. I did that specifically just so they'd be easier to identify when we're looking at the stack. And go, oh, okay, that's where variable A is, variable B, variable C. And the same with 111. But it starts out in main, initializes a variable, and then sets that variable equal to whatever's returned from cool, and then adds itself to it. Cool itself has initializes 3 variables, then adds A to B and puts the result into A, and then subtracts C from A and puts that in C, and then returns that value to C for the value that's added back in. So over here on the left-hand side, this is the tool that I use it's GDB, which is a command line debugger for Linux. And I have this plugin in it which just kind of enhances some of the information that it has, makes it more readily accessible while you're stepping through. It's real good when you want to see exactly what's going on at the bits and the bytes. So just kind of run it the same way you do. I did compile this program without most of the extras, so it's just a straight 32-bit program, so it'll look like the stuff that you guys have been going over in class. I'm going to set a breakpoint for main, and then run it. Okay, so we got a bunch of information here. Code-wise, it's stopped execution right here where it's going to initialize the variable. So this is the C code down here. Up here is the assembler, what's going on assembly-wise, what those instructions look like. Up here, this is the stack. It is ordered in the same way that you guys think about it in class. So it's going, the larger numbers are at the top and the smaller numbers are at the bottom. So when the stack expands, it goes down, expands down. And up here are the different registers. We have EAX, EVX, all of those. ESP you guys have talked about in class quite a bit already. That is tracks where the stack is in memory. And then EBP is the base pointer. It's kind of where the stack starts for the program, for whatever function you're in. And the other one that we'll talk about a little bit as I'm going through this is the EIP. Does anybody know what that stands for? Have a guess? EBP, BP is base pointer, ESP, SP is stack pointer. Notice how this value 3FO is similar to the address of that value there. See how it's got the same value. The EIP has the same value there as it does here. Still nothing? What is this called? What is this itself called in assembler?
We drove on the lights and turned for me that part
Yeah.
with the lines actually staying.
Is that any better? Might need to scoot up. because I'm trying to get all the information on the screen, and this poor printer, I mean, display only supports so much.
You can both lines, right?
Those are probably as close as we can get. I don't know why it's so washed out today. Oh yeah, that could not be helpful. That do anything? Yeah, I don't know. Well, it's off to the side like it always is, but it's miserable. It's just. Oh, we only got one light on, but. Huh. I can try scooting it over, because clearly it's better displayed on that side, but. We will. Is that better?
Yeah.
Is that readable at all there? On this part? What about if is it more readable now?
Yeah.
Over there? Okay. Because I really wanted them on the same page, but can only do what we can do. I can. No. It's still not. Really need those to go to 3 lines, and we just don't want to. Let's see. Not cooperating at all, is it? There we go. Wow, why do I have to go all the way over there? It's crazy. Put this. It's about the best I'm going to get. Okay. All right. So with the way this is laid out, again, these are the registers. This is the EIP. And then down here we can see that the 3F0, that these two are the same. So what's this probably called? Or what is this right here? What is the move D word? What do you call that in assembly? You guys remember?
In the last touch.
So in the assembly, this is considered an instruction. So each one of them, so like you have commands like, to go to the next one, I'll be using a lot SI, which is step instruction. So this guy up here stands for, the IP stands for instruction pointer. Okay, moving on. We have this, so these two lines line up. We're initiating this variable and main1, and what we're going to do is we're going to move 111 into EBP -4. So let's look over here at what's going on. The program, the EBP is pointing at 38. So I've just truncated it over here to 38. And that's where we're pointing right here. That's the EBP. So for this program, that is the base pointer. When you make references, when it does the minus, because remember this going down is we subtract, EBP -4 is going to be the location of main1, or this variable for main. And then we're setting it, we're moving that hard-coded value into main1. So once this command executes, we can see that on the stack right here at the top of the stack, we have the value for main. So this is where main is going to be located for the rest of the program. The EIP incremented to the next one, so it's at F7, which is this call. It's going to call our cool function. And then we're on this line right here. Notice the next command is this add command, so it's doing this part right here. That's where we want to come back to. So once we're done with cool, we're going to come back and execute it just kind of like you think about with a normal program. But we basically have to save that somewhere. We have to save this location, this 3FC location somewhere. And it's saved, and you guys will get into this in class, based on the calling conventions, it's saved on the stack. So the call command not only moves the EIP so that we're at the beginning of the new function, it also puts where we're leaving the next command that we're going to go to onto the stack. So now we're at the start of cool. You can see over here the definition of the function in the codes where we're pointing at, and we're at this command here. So these three commands are part of the calling convention as well. They're going to do three things. They're going to add the EBP that was from main. They're going to add it into the stack so that they can get it. We can get it back once we return from this function. And then it's going to move the EBP equal to where the stack pointer is, and then it's going to subtract from the stack pointer to make room for all the local variables. So you'll have the variables that are going to be used in this function framed by the EBP on top, which will be a larger number, and the ESP a little further down, which will be a smaller number. So over here, we added the 111. Now, after the call, we have the stack set up like this. The EBP from main is set to that. We haven't done anything with that. But this value was pushed by the call. So the return to main, where we're going to return into main. And the actual value is this 3FC. And it shows you, my program shows you, okay, this is pointing to that add, the add command that we were talking about up there. And these are saved on the stack so that we can pop them off later and get back to exactly where we were in the program, with the state being the same, the program being in the same state. And all of that's stored on the stack. Now, when we're doing attacks against programs, buffer overflow attacks in particular, this saved EIP is usually what we go after, where it's saved. So when the program returns, instead of jumping to where it's expecting to in main, we can have it jump to anywhere we want. And that's commonly where we get that from. So the next thing it's going to do is it's going to save that EBP. So it saves, oops, yeah, it's going to save, the call saved the command, and then it's going to save the CD38 onto the stack as well. So we see it put the CD38 here, which is what was in EBP, and then it's going to set, and now it's going to set the EBP up here. It's going to move it down to wherever the ESP, wherever the stack pointer currently is, which is down here pointing at that location. We can see once we do the move. And then the last one, this subtract, we're up here on the stack with the stack pointer pointing to here. We want to move it down so that it frames out where our local variables are going to go. Oh no, the spacing is off. So it creates these three, don't mind the extra spaces. I'm hopeful, yeah, they're not completely permanently there. So by moving the ESP down, we take it to CD20, it made room for these three local variables for pool A, B, and C. We can see how the stack's now pointing down to 20, and why, if we just created this new space on the stack, why are there already values on the stack? Just some kind of guess. Be good? Yeah, it's just junk from whatever used the stack previously, didn't clean it up. So some program at some point was executing in this area, was using the stack, and it just put it all, just left it there and didn't worry about it. So that's why you can, if you don't initialize variables, you can get all sorts of random stuff in your variables in C. And this is why right here, because when it allocates the stack for the local variables, it doesn't clean it up or do anything with it. Cool. So when we execute each of these, you'll see I did the A, so now that first one is set to A, second one is set to B, and the third one is set to C. So we now got these variables in here, and you can still see our variable from main that's actually up here with these two saved values, automatically saved values in between. If we look over here, this is after initializing all three variables. You have A, B, and C. And some extra space. All right, I'm going to fix that real quick. fix anything. Just my display being upset. All right. So the next command, what we're going to do is we're going to move. So let's look over here. So cool A is referenced by the EBP -4. This is the typical way that locals are accessed. It actually does it from the point of reference of the EBP and not from the ESP. So it subtracts down. So you have EBP -4 is cool A, EBP -8 is BBB, and EBP -C, which is 12, it holds the next one. So each of them are spread apart by 4, because they're 4 bytes. They each can hold 4 bytes. They're integers, just standard 32-bit integers. But there's cool A, cool B, cool C. So the next thing that the program does is it takes EBP -8 and it moves it into EAX. It's doing this so that it can work with it. It's going to, then on the next command, it's going to do an add command where it adds it to the -4. If we look at the code down here, we're adding A to B. A is -4, B is -8. So it goes ahead and it moves -8 or call B into EBB. So once this command executes, we should see that EAX is now equal to BBBB. If you look up here, it changed, and it is. Same with over here, EAX is BBB. It came from this green location. The next thing we're going to want to do, or the next thing the program does, is it just adds the 2 variables based on that command there. So it's adding A to B. B is already stored in EAX, so it's going to add the value in EAX to cool A, and it's going to store that value in cool A. Just like that assignment and add does right there. So we look up here, cool A now has 16665 for its value, and same thing over here, looking at the stack from this view, we've changed this value, and EAX was used, added it to itself, and we ended up with this new value in cool A. The next thing we're going to do is move from EBP -4, which is cool A, so this value here, we're going to move it into EAX. So the 1665 overwrote, if we look, it was BBBB before, and now it's 1665. And then the same thing's going to happen over here. 1665 is now in the EAX, and then we're going to subtract from that value, we're going to subtract the value in the third area, or cool C. It's going to be subtracted from the 1665, and it's going to, thanks to the comment, it's going to give us 9999 stored into EAX. So it's not, it doesn't do it directly into cool C. But it will on the next one. It'll move it back there on the next step. So the subtraction, we now see that it's got 9999 in there, and then it's going to move that value back into C. So C now has that value. See the same thing over here. This is used to subtract. We end up with the 9999, and then we take the 9999 and we copy it and we put it into this value here. So when a program returns values, it uses in this calling convention that you guys will use in class. So for how functions are called and how they return in this class, they will always be, it'll be up here in EAX. So the value's copied into EAX and then returned, and then the program can access it. That's how values are returned, because as soon as we get to the end of execution, this whole stack will be gone. It'll be turned into junk. And there won't be anything usable there that we can get from it. So it moved, that's why it moved it back into EAX. It moved the value back in there. It has to compile this without knowing what the actual value will be, which is why it doesn't do something a little smarter where it could maybe save a step or two. All right, next step. So when there's two high-level assembler instructions that are executed when you're leaving a function, a leave and a return. The leave actually has built into it, it does two things. The first thing that it does is it moves the ESP back up to where the EBP is. So it's going to, if we go back up here, it's going to take ESP and it's going to move it from CD20 up to where EBP is. So all of this down here will be considered junk at that point and won't appear anymore. So we have EBP pointing to the same place as ESP. And then, and that's what's happening with this command. The second thing that it does is that it pops the EBP. So looking at the last command, we're here, and if a pop is done, ESP is going to be moved up to this location because that's what happens with a pop. ESP is incremented. It's moved up when you pop something off the stack because we're losing this part of the stack. And then whatever value in here is going to be loaded to EBP. This was the value that pointed it all the way up to here. So we should see it go to CD38. That's the saved value for mains EBP. And if we look, ESP moved up. So it was at 2C, but now it's at 30 ESP, and EBP has moved up to here and is pointing at its old place where it was when we started in main. And EAX is just kind of hanging out there. Nothing's happened to it, but we're going to use it. We know it's going to be used in main. And then the next thing that's done is a return. The return looks at this next value here, and it pops it into that EIP I was telling you about. So the EIP is what instruction's currently being executed, and it directly just pops from EIP, or it pops from the stack into EIP, this saved value. So it's going to take us back, and it's going to make the program be pointing at that add that was right after the call. Cool. And so yeah, the EIP is now equal to the whatever value for the next command after call. When we look over here, oh, I already did it in the last step. When we did the return in the last step, the EIP is going to become whatever this 3FC value is, or it's going to become that 3FC value pointing to the next one. And then after it's executed, EIP is now equal to that 3FC, so we're currently here. Since we popped it, the actual stack pointer moved up a little bit, moved up 2. And so now it's back. The top of the stack is our local variable, so everything's kind of back where it was before we left, and we're ready to do the final add. Now with this add, it takes that value from EAX that we saved, so the 9999, and it's going to add it to the local variable, which is EBP minus 4. That's this guy right here. And so after the add, the EAX is going to be 9999, and the new value is going to be 4 A's. So looking on the stack right here at the top, that 1111 became AAAA. And then we're done. It's doing this. Can anybody venture a guess why it's moving 0 to EAX before we leave? Before we leave main? What's the last command in the C program there?
Return 0.
Yeah. So what register did I say a little earlier? What register holds your return value? Yeah. So this command is just setting the return value, whatever the return value is, so that the program can return. It works the same way. Like when your program is called from the operating system, all we do is we go off that branch, we execute it, and then it returns back to the operating system, whatever spot it left off from. In this case, that would be this libc start main, and it would do its own adjustment to its ESP. But that's part of the going back to the operating system. That's not necessarily, it's close enough. But that's kind of the basics of how everything executes related to the stack. Sets it to 0. And we're done. Any questions? On the exam, you guys will get, a block of code basically, and have to show what the stack looks like after the code's executed. So kind of the same thing. You won't have to do the coloring, which was a huge pain, but to make stuff stand out a little better.
Yeah, you have to bring different pens for.
Exactly. Highlighters, when I've gone through complex assembly code, highlighters are your best friend. I mean, just for seeing stuff that it's hard for us to pattern and pick out. I have my 3 colors of highlighters with a pen and a pencil usually. So,